Okay, so now we talk about the double slit experiment. This is going to be more of a conceptual talk than an actual calculation, but it is an important one because it establishes something that um, can be considered one of the main tenets of quantum mechanics. So as I explained earlier on, if you shoot electrons at a double slit, with the assumption that electrons are particles, we would have expected to get only signals specifically at the point where the slits are open, meaning the places where the electrons will actually pass through. But instead we get this wave diffraction pattern, which is explained and observed experimentally to happen with actual light waves. So things that we associate with wave character do generate this type of pattern as they pass through a double slit. This is something known as the Young experiment, and for those of you who are taking or will be taking physics, you will cover this within the chapters that do talk about waves and the wave character of light and sound. But the idea is that electrons that up until this point were thought of just being particles and behaving as particles are now exhibiting patterns of wave behavior. And this was actually rather puzzling and something that could not be explained using classical mechanics. And so the interesting thing is that the fact that we get signals showing up at places where the slit's not open can be definitely explained by the idea that when the waves kind of propagate outwardly as they pass through the slits, if they do in fact behave as waves, there will be spots in which the waves will constructively interfere each other, yielding to a higher rise in the amplitude of the signal. And there will be other regions where there will be destructive interference, meaning that you see no signal. And so you kind of create this nice pattern in the detector screen over here. And this is actually what leads a different scientist, de Broglie, to pretty much make the connection that matter it's actually got both wave and particle counterparts to each other, and they're both part of the same. So there's this duality in matter, which de Broglie basically in simple terms expressed with the following equation. Specifically, Planck's constant, yet again, that natural constant of quantum mechanics. Planck's constant is the combo of the momentum of a particle, which is associated with the particle character of anything, times the wavelength of that specific particle. Now, this is associated with the wave-like character. So this simplistic equation actually contains this central tenet of quantum mechanics, that in the quantum world, in the very small world, in the nanometer scale world, you actually have particles behaving like waves, waves behaving like particles, and they are both part of the same thing. It just so happens that in certain circumstances the particle behavior takes place, and in other ones the wave behavior takes hold. So it's one of the interesting things about quantum mechanics. But matter basically has a duality, a particle-wave duality. This is what was observed through the experiments and is explained by de Broglie's equation. Another thing that also presents itself is the Heisenberg uncertainty principle, which basically arises from the fact that because you're dealing with waves and there is probabilities of the waves interacting constructively and destructively at certain places, you don't actually have a concrete, unique answer to a quantum mechanical problem. In fact, it's more of a statistical problem where you are basically saying, we have 50% chance of this happening, or we have 60% chance of this happening. It doesn't mean that it's going to happen, but if you place your bets on it, you have a better chance betting for the event happening with 60% probability than not happening. But nonetheless, it is not a concrete value, and this is kind of what the Heisenberg uncertainty principle says right here. For a set of variables that are commutable with each other, there's actually a maximum level of precision that can be attained when you measure one or the other. And there's actually an effect in association with each one of them. And we're going to investigate these aspects next. So Let's get to it. Let's talk about the Brawley's equation and see what actually um, happens in terms of calculations. Okay, so the equation as given is Planck's constant equating to the momentum times the wavelength of the particle. Okay, a few things that need to be said. The Planck's constant itself is in joules times second. The wavelength here has to be expressed in meters specifically, and the momentum, which you might have not seen until now, especially if you haven't taken physics, is given by the mass of the particle in kilograms times the speed or velocity of the particle in meters per second. So momentum has units of kilogram meters per second. And when you multiply momentum by wavelength, you end up getting units of kilogram times meter squared over second, which is ultimately the same thing as saying kilogram meter squared over second squared times seconds. In other words, the units are the same on both ends, kilogram times meter squared over second. Okay, so now let's take a look at an example. Let's find out at what speed an electron must travel to have a wavelength shown in here. Okay. Now, in order to do that, we have to account for the fact that an electron has particle and wave characters associated with it. Specifically, we have the Brawley's equation to account for it. So knowing the wavelength of a traveling electron allows us to calculate the momentum of that electron. So what we're going to do is plug in Planck's constant, 6.626 times 10 to the negative 34 joules, and we're going to divide that by the wavelength, 0.7 angstroms. Here we have to make sure that the, first of all, we're going to convert the units of joules to kilogram meter square over second square, which means that Planck's constant will be in kilograms meter square over second. And secondly, we need to change the angstroms to meters. And we know that for every meter, there is 10 to the 10 angstroms present in there. So the angstroms will cancel out. And you will notice that the meters will partially cancel out, and they will leave behind kilogram meter per second, which are units of momentum. So multiplying the two numbers together and dividing by 0.7 yields 9.47 times 10 to the negative 24 kilogram meters per second. Alright, now what we want to find out is the speed of the electron. So what we need to do is account for the fact that just by looking at the units, momentum is mass times velocity, or mass times speed. So in order to find the speed, we need to divide the momentum by the mass of the particle. And since the particle is the electron, you need to use the mass of the electron. Now this is a value that I will have to provide you with in problems of this sort, because you will not be expected to know it, at least not by memory. Alright, needless to say, 9.47 times 10 to the negative 24 kilogram meters per second gets divided by the mass of the electron, 9.031 times 10 to the negative 31st kilograms. The kilograms will cancel out and they will leave behind meters per second, units of velocity or speed. Here I would highly, in fact, not only do I recommend, but I think it's a prerequisite that you do use parentheses around the exponential numbers because you're doing a division. If you don't do that, there could be some problems with your calculation. But if this is done correctly, you should end up finding out that the speed is 1.05 times 10 to the 7 meters per second. Now, the calculation, as you can see, is not too difficult. I would recommend that you keep track of the actual units. But one thing that I kind of want to highlight is that this particular wavelength corresponds to X-rays themselves. This is the wavelength of X-ray sources of light. And you can actually produce it in the following way. If you have an electron which is accelerated towards a positively charged voltaic plate, typically either made out of molybdenum or copper, if you basically speed up the electron high enough so that you reach, partial velocities that reach to some degree, a degree, well, maybe not a degree, but just a fraction of the speed of light. They're traveling very fast. That's kind of what I'm saying. Upon collision of the electron with the metal surface, you will produce rays of light that correspond with the speed of the electron. In essence, you have basically turned that speed of the electron with the collision into the wavelength of light that the de Broglie equation basically describes. And so just by that simple collision of fast-moving electrons onto a metal surface, you generate X-rays. And the X-rays have a specific attribute to them that is very helpful to chemists. Specifically, the wavelengths of X-rays fall roughly in the vicinity of bond lengths for molecules. If you actually shine X-rays of X-ray light onto a crystalline solid of some sort, this will create a diffraction pattern that ultimately can be mathematically deconvoluted back to the actual structure of the molecule. And this is one of the ways in which we determine how a molecule looks like. And by the time you guys take physics, you'll probably get enough exposure to this type of thinking that you come to appreciate, diffraction analysis. But for now, this is where I'm going to stop it. On the next video, we'll talk about the Heisenberg uncertainty principle.